Welcome to the e-lecture session for diploma students. In today's class, we are going to deal with some of the basic components and some of the basic fundamentals of electrical machines 1. Electrical machines 1 is the most important and essential ingredient of an electrical engineer. Faraday's laws of electromagnetic induction, Lenzs law, types of DC generators, classification, principle of operation, constructional details of a DC generator are the major areas, thrust areas upon which the entire session is focused on. Firstly, we will deal with the DC generator. DC generator is a machine which converts mechanical energy into electrical energy with the magnetic field as the coupling medium. It works on the principle of Faraday's law of electromagnetic induction. So, this is basically a block diagram which shows how a DC generator works. Constructional wise, a DC generator is same as that of a DC motor. We commonly call it as a DC machine basically. So, this is the block diagram. The prime mover is coupled with the electrical generator here. The prime mover draws supply, that is electrical supply from the supply mains, which is given as energy block diagram. So, the prime mover converts, that is the prime mover gives out the mechanical energy being coupled to the prime mover, the electric generator generates the electrical energy. In all the electrical machines including the transformer, magnetic field is used as a coupling medium for energy conversion and transfer. Hence, it is very important for us to know the basic concepts of electromagnetism before going into the details of Faraday's law of electromagnetic induction. Basics of electromagnetism: magnet and magnetism. A substance that attracts pieces of iron and steel is called a magnet, and this property of the material is called magnetism. Magnetic field: the magnetic field is the area around a magnet in which there exists a magnetic force. Then comes the magnetic flux. Magnetic flux is the number of magnetic lines of force emanating from a magnetic material. It is represented by a symbol phi and its unit is Weber. Magnetic flux density: the magnetic flux density is nothing but it is the flux per unit area at right angle to the flux. It is represented by the letter B and its unit is Weber per meter square, or we can call it as Tesla. So, the magnetic flux density expression is given by B is equal to phi by A, where phi is the magnetic flux and A is the area of cross section. Then comes the permeability. It is defined as the ability of the magnetic material to force the magnetic flux through a given medium. It is represented by a letter mu and its unit is Henry per meter. So, the expression of permeability is mu is equal to mu naught mu r, where mu naught is the permeability of free space or air and mu r is the relative permeability of medium with respect to air. Mu naught is given by the value 4 pi into 10 power minus 7 Henry per meter. Then magnetic permeability is the opposite of magnetic reluctance. Then comes the definition of reluctance. It is the property of the material which opposes the establishment of magnetic flux in it. It is represented by the letter S and its unit is AT per Weber. AT is nothing but ampere turns per Weber. S is equal to mmf, that is magnetomotive force, divided by flux, magnetic flux, which is also given by the expression L by mu A. Then magnetomotive force mmf. In an electric circuit, an electromotive force is required to produce a current flow. In magnetic circuits, magnetomotive force is required for the flow of flux. It is the product of number of turns in the winding and the current flowing through it. It is a measure of how much excitation is being applied across a magnetic circuit. The force which causes the magnetic flux in a magnetic circuit is called magnetomotive force, and the unit of magnetomotive force is ampere turns. MMF is equal to N into I, where N is the number of turns of the coil, I is the magnitude of current which is passing through the coil. Then we can come to the Coulombs law of magnetic force. When two isolated poles are placed nearer to each other, they experience a force on each other. First law, it states that like poles repel each other while unlike poles attract each other. The second law, the Coulomb's second law, states that the force between two magnetic poles is directly proportional to the product of their pole strength and inversely proportional to the square of the distance between their centers. So, F is directly proportional to product of M1 and M2 divided by the distance between the two, that is the square of the distance between the two, where M1 and M2 represent the magnetic field strength of the two poles and D represents the distance between the two poles. From this definition, from this second law definition, we come to the conclusion that suppose if the distance between any two poles is higher the distance between the poles, lower is the force. When an electric current flows through a conductor, a magnetic field is set up all along the length of the conductor. Number 1, the greater the current flow in the conductor, the stronger is the magnetic field and vice versa. Number 2, the magnetic field near the conductor is stronger and becomes weaker and weaker as we move away from the conductor. Thirdly, magnetic lines of force around the conductor will be either clockwise or anti-clockwise depending on the direction of current. Right hand thumb rule is used to determine the direction of magnetic field around the conductor. Fourth point, the shape of the magnetic field thus obtained depends upon the shape of the conductor. Here is the illustration of right hand thumb rule. Hold the conductor in the right hand with the thumb pointing in the direction of the current as shown in the figure. Then the fingers will point the direction of the magnetic field around the conductor. Suppose if you assume this to be the conductor, the current is flowing from this end to this end, you keep your thumb here in the direction of the current and wrap around all the fingers around the conductor. If this thumb represents the direction of the current, then these 4 fingers, the remaining 4 fingers will give you the direction of the magnetic field. Suppose if the current is flowing from this end to this end, then you should keep the thumb like this, should wrap around the remaining fingers like this. So, the thumb will give you the direction of current and this will give you the, that is the magnetic field direction will be entirely in the opposite direction, the other way around. So, this is what the right hand thumb rule implies. Here is one more notation called as cross and dot notation to find out the direction of magnetic field lines. Cross and dot notation can also be used to indicate the direction of the current flow. In the figure 1.4, the current flowing away from the observer is indicated by the cross. The cross is based on the tail of an arrow moving away from the observer. Figure 1.4 also shows that the current flowing towards an observer and is indicated by a dot. So, this is the dot and this is the cross. The dot is based on the point of an arrow moving towards the observer. Then comes the Faraday's laws of electromagnetic induction, which forms the basis of the working of a DC generator. A DC generator works on the principle of Faraday's law of electromagnetic induction. Here comes the Faraday's experiment. Consider a coil C of several turns connected to a central 0 galvanometer as shown in figure 1.5. If a permanent magnet is moved towards the coil, it will be observed that the galvanometer shows the deflection in one direction, either this direction or the other direction. If the magnet is moved away from the coil, the galvanometer again shows a deflection, but in the opposite direction. The deflection of galvanometer indicates that there is a current flow through the coil. For the current to flow, there must be an EMF in the coil. Hence, it is concluded that when magnetic flux linking a conductor or coil changes, an EMF is induced in it. Faraday's laws of electromagnetic induction. First law: whenever the magnetic flux linking a conductor or coil changes, an EMF is induced in it. Second law: the magnitude of the EMF induced in a conductor or coil is directly proportional to the rate of change of flux linkage. Here the minus sign on the right hand side represents Lenzs law. So, induced EMF E is directly proportional to d phi by dt. D phi by dt is nothing but it is the rate of change of flux linkages with respect to time. Then E is equal to, that is induced EMF is equal to minus n d phi by dt. So, this minus sign is indicative of the Lenzs law. N is the number of turns of the coil, d phi by dt is the rate of change of flux linkages with respect to time. Then direction of induced EMF and current. The direction of induced EMF and current can be determined by one of the following two methods. One is Lenz's law, the other one is Fleming's right hand rule. Firstly, we will see what Lenz's law states. The induced current will flow in such a direction so as to oppose the cause that produces it. In this case, the cause for the induced current is the increasing magnetic flux linking the coil. Therefore, the induced current will set up a magnetic flux that opposes the increase in flux through the coil. Fleming's right hand rule. This law is used to find the direction of the induced EMF of DC generator. Hold the forefinger, middle finger and thumb of the right hand so that they are at right angles to one another. If the forefinger points the direction of magnetic field, this is the forefinger. If this particular forefinger represents the direction of the magnetic field and the thumb the direction of motion of the conductor, then ultimately the middle finger will point the direction of the induced current. You have to stretch out your fingers like this, mutually perpendicular to each other. So, thumb should be mutually perpendicular to forefinger as well as the middle finger. Faraday's law states that whenever a conductor cuts the magnetic flux, an EMF is induced in the conductor. Therefore, the essential components of a generator are: number 1, the magnetic field; number 2, conductor or a group of conductors; number 3, motion of the conductor with respect to the magnetic field or the prime mover. For the generation of induced EMF, there should be a relative motion between the conductor and the magnetic field, that is, either the magnetic field should be moved while the conductor is being stationary, or the conductor is made to move in a stationary magnetic field. Either of these two should happen for the generation of induced EMF. Either the conductor should move or the field, that is the magnetic field, should move when the other one is made stationary. When the magnetic flux linking a conductor changes, an EMF is induced in the conductor. This can be done in two ways. One is the dynamically induced EMF, the other one is statically induced EMF. What is the meaning of dynamically induced EMF? If the conductor is moved in a stationary magnetic field, then the EMF is induced, the EMF induced is called dynamically induced EMF. Example, the EMF being generated in a DC generator. In that the conductor is moving, that is the armature will be rotating, whereas the magnetic field remains stationary. The second case is statically induced EMF. If the conductor is stationary and the magnetic field is moving or changing, then the induced EMF is called statically induced EMF. Example, transformer and AC generator, that is alternator. Now, we will see how the DC generator works. So, working principle of a DC generator. The method of producing EMF in a single loop generator is explained in the figure 1.7. Figure 1.7 shows a single loop copper coil ABCD. So, this is A, B, C and D, ABCD moving in a magnetic field. So, this is the magnetic field. So, this is the north pole, south pole. So, between these two poles there exists magnetic flux lines called magnetic field. The two ends of the coil are joined together to two slip rings. So, here is a slip ring 1, here is a slip ring 2. These slip rings are insulated from each other. Two collecting brushes are pressed against these two slip rings. The brushes collect the current induced in the coil and supply it to the external load. So, this is the external load. When the coil rotates inside the magnetic field, the flux linked with the coil changes and hence the EMF is induced in the coil, which is proportional to the rate of change of flux linkages. Assume the coil is rotating in the clockwise direction. So, this is the coil, one which appears in a rectangular form is the coil. It is, for illustration purpose, it is shown as a single coil, but normally the armature contains many coils. When the plane of the coil is at right angles to the flux lines, that is in position 1, where theta is equal to 0 electrical degrees. So, this is the position 1. So, this point is a position 1. So, we are going to assume the coil to be at position 1, that is the coil side AB is at the top and the coil side CD is at the bottom. So, if the position of the armature is like this, then the flux linked with the coil is maximum, but the rate of change of flux linkages is minimum. That is, the flux lines being cut by this coil side, or that is the coils ABCD is minimum, but the rate of change of flux linkages is, so that is the flux linked with the coil is maximum, but the rate of change of flux linkages is minimum, because in this position the coil does not cut any flux lines. Therefore, no EMF is induced in the coil at position 1, because E is nothing but minus n d phi by dt. We have already seen this. So, whenever d phi by dt is 0, ultimately the expression for induced EMF becomes 0. That is what it implies. Working principle of a DC generator. Here the position of the coil is going to be changed here. So, earlier it was in the position of 1, now it has come to this position 4. So, this is the position where the coil is right now, and when the coil moves to position 4, which is indicated by angle theta is equal to 90 degrees, the coil plane is horizontal to the flux line, that is the flux linked with the coil is minimum, but the rate of change of flux is maximum. That is, here in this position, this is where exactly the position of 4 is there. So, in this position d phi by dt is maximum, whereas phi is minimum, that is 0. When again the plane of the coil moves from horizontal to right angles to the flux lines, that is position 4 to position 7, that is it moves from the angle 90 electrical degrees to 180 electrical degrees. The flux linked with the coil gradually increases, that is here. Now the position of the coil is here. The flux linked with the coil gradually increases, but the rate of change of flux linkages is minimum, because in this position coil does not cut any flux lines, therefore, no EMF is induced in the coil at position 7. So, this is the final position. Now, if the coil moves from position 7 to 10, that is 180 degrees to 270, then the EMF induced in the coil is in the reverse direction, that is the EMF will be on the negative part. Therefore, so this is the 10th position, position number 10. Therefore, at position 7 the EMF induced is negative maximum, then the coil moves from position 10 to position 1, that is 270 electrical degrees to 360 electrical degrees. The flux linked with the coil gradually increases, but the rate of change of flux linkages decreases. So, summarizing everything, we can say that, so this is how the voltage will look like, right. So, this is position 1, this is position 1, this is 4, this is position 7, position 10 and again position 1. So, when the coil is at position 1, the EMF is 0, we have seen that. When it goes to the position of 4, then the voltage is increasing to the positive peak, it attains positive peak at exactly at 4, and when the coil attains the position 7, it comes back to 0, the EMF is 0, and from 7 to 10, when the coil moves from 7 to 10, position 7 to 10, then the voltage is maximum again, but in the negative direction. So, this is minus V, so this is positive plus V. Again from position 10 to position 1, again it becomes 0. So, this is the entire half cycle. So, this is positive half cycle, this is the negative half cycle. Even if the generator is a DC one, the EMF being induced is a alternating one, and we need to convert that alternating voltage to equivalent DC voltage with the help of split rings and commutator. That is what we are going to see next, conversion of AC to DC. If the slip rings are replaced by split rings, the alternating EMF will become unidirectional current, that is DC. The split rings are made out of conducting cylinder which is cut into two segments insulated from each other by a thin sheet of mica. The coil ends are joined together. To these segments, the carbon brushes rest on these segments. Here the figure 1.8 shows the connection of coil ends with slip rings A and B. In the first half revolution, current flows along A, B, L, M, C, D. So, this is A, B, L, M, C and D. In the brush number 1, which is in contact with the segment A, which acts as the positive end of EMF, while the segment B acts as the negative end. So, these are the various positions, we have already seen this as a separate positions, whereas here for illustrative purpose we have drawn all the positions of the coil in a single diagram. So, this is position 1, position 4, position 7, position 10 and then position 1 again. So, here is a positive half cycle, here is also, here it is a negative half cycle. So, we have converted this to DC with the help of a split ring and commutator. In the next half revolution, the direction of current in the coil has reversed as shown in figure 1.8, but at the same time the positions of segments A and B have also been reversed. The segment A is coming in contact with brush number 2 and becomes negative end of induced EMF. Again, the current in the load resistance flows in the same direction from L to M. Hence, the current is unidirectional current. The AC induced in the coil is converted into unidirectional current due to the rectifying action of the split rings, also called as commutator. The unidirectional current thus obtained is shown in figure 1.8. To minimize the ripple in the DC current, the number of coils in the armature should be increased. So, definitely there will be some ripple, harmonics present in the DC obtained. So, in order to reduce that, the suggestion is we should increase the number of coils present in the armature. Then comes the very important topic, construction of a DC generator. A DC generator can be used as a DC motor without any constructional changes and vice versa. Thus, a DC generator or a DC motor can be broadly termed as a DC machine. Figure 1.9 shows the constructional details of a simple 4-pole DC machine. It consists of two basic parts. One is the stator, the other one is a rotor. The major constructional parts of a DC machine, the first one being yoke, poles and pole shoes, thirdly field winding, armature core, armature winding, commutator and brushes. In today's lecture, we have seen the laws of Faraday's laws of electromagnetic induction, Lenzs law, then the basics, very basic fundamental points of DC generator, etc. Thank you.